Hello everyone, hope you are doing good. Welcome back to another video lecture on Strength of Materials 1. So we are in first unit. So today we are going to learn an interesting topic called strain energy. Strain energy. What is strain energy? We already learned about strain. Now the another term is added, that is strain energy. Right? So whenever the body is strained, that means whenever the external load is applied, there will be some deformation, right? There will be some deformation in the length of the material. So when you try to strain this material, when you try to pull axially and within this elastic limit, this will come back, right? Within the elastic limit, when you release the load P, the material will come into original position. So till the elastic limit, when you apply the load, this material will have some energy, which will hold some energy, and that energy is known as strain energy. So let me define here so that you can understand. So whenever a body is subjected, or let's say the body is strained, the energy is absorbed in the body, right? So it is strained, the energy is absorbed by the body. The energy which is absorbed in the body due to strain effect, right, or straining effect, is known as strain energy. So what is the best example for strain energy in real life? So let us take a spring, right? If I take a spring, if I apply a compression load here, it is get contrast, right? Now again suddenly if I release the load, it will come back its original position by bouncing it back, right? That energy is absorbed when the material is strained, right? When the material is strained, there will be some energy which is absorbed by the material, then it will release the energy when the load is removed, right? That energy is known as strain energy. So in other words, I can define as the strain energy is the stored energy which material deform within elastic limit. I can write here the strain energy to be stored when material deform within elastic limit. So it will only store the energy within elastic limit, right? So one more example of this, a great example, that is a bow and arrow, right? A bow and arrow is a great example for this, right? So when the energy, that means when you apply the tensile load from here, let's say P, and suddenly if you release the load, it will have some energy absorbed and then it will release with a force, right? That force is nothing but the straining force, right? This bow and this arrow will get some energy, the strain energy, which is stored in the arrow. It's a great example. We'll see some formulas related to this. In the syllabus, in the JNTU H syllabus, we need to learn about certain applied load. So let us try to memorize these formulas so that it will be easy in your numericals. So the load is applied on a material can be, so these are the basic loads which are applied on a material, right? The first one is gradually applied load. Gradually applied load. So what is gradually applied load? The name itself says that it will apply step by step, right? Some load, for example 5 kilonewton, then 10 kilonewton, 15, 20, like that. It will increase the load gradually. So the load is named as gradually applied load. The next one we have suddenly applied load. Suddenly applied load, right? So sudden applied load, suddenly the load is applied or suddenly the load is going to increase. Next we have impact load. Impact with great potential, the energy will come and hit the material. So let us, for example, something is falling suddenly, like something is falling from certain height. That means it is carrying the energy and it is falling, like hitting the material. That is load falling from a height, right? So these are the three loads, three kinds of loads which we are going to apply on the materials, right? Let us see that the strain energy is denoted by U, small u, right? And the U and the equation is given as sigma square upon 2E multiplied by V, and the units are Newton, mm, right? So here U is the strain energy, sigma is the stress, and E is the Young's modulus, and V is the velocity, V is the volume. Can write here V, volume of the material. So volume, it is three dimensional, so the units will be mm cube, right? Mm cube is the volume and E is the Young's modulus. Let us understand resilience. What is meant by resilience? Resilience. Yes, so it is strain energy. It is defined like the total strain energy stored in the body. It is commonly known as resilience. Total strain energy. Let us write here the total strain energy stored in the body, right, is commonly known as resilience, right? Simple to understand. Let us remember the total strain energy so that you can relate to this resilience, right? So whenever the straining force is removed from the strained body, what will happen? The body will capable of doing some work, right? The body is capable of doing some work. Hence the resilience is defined as, right, you can write here, whenever the strained body or straining force is removed on body, the body is capable of doing some work, right? Hence the resilience is also defined as the capacity of the strained body from doing work, right? The capacity of strained body defined as the capacity of a strained body for doing work, right? So this is called resilience. So again I will try to repeat in simple words. When the total energy stored in the body is commonly known as resilience, right? Clear? Now when a material is strained, the straining force will applied on a strained material or body, it will have a capacity or capable of doing some work. When it is going to release, if you remove the load, it will capable of doing some work. For example, like bow and arrow, if you try to strain the bow and you're ready to aim on something and it is ready to do some work, right? If you release, it will push the arrow towards the target, right? So that capacity of strained body for doing work is known as resilience, right? Let us clear this. Let us understand. Proof resilience, right? Now we understand what is resilience. Now we'll try to understand proof resilience, right? So this is defined as the maximum strain energy stored in the body. Okay, so the maximum strain energy stored in the body is commonly known as proof resilience. The maximum strain energy stored in a body is commonly known as proof resilience. Right? Now, the strain energy stored in the body will be maximum. When it will be maximum? When the body is stressed up to its elastic limit. Remember this word. When the body is strained or stressed up to the elastic limit, this is under the elastic limit. That means this case will only applicable within the elastic limit. So that I can write now the strain energy stored in the body will be maximum. When will it be maximum? When the body is strained up to elastic limit. Right? Is known as proof resilience. Now I can write the proof resilience means maximum strain energy. Right? Now you got it? Now we'll see our formulas for different load in different cases. Let us write here stress in member of different cases. So the first one is the gradually applied load, right? Gradually applied load, right? So let us consider a graph, so where deflection on x-axis and load on y-axis. Load P, deflection, let's say delta L. So it will be go linear because it is applying gradually, step by step. So this area and the energy which is stored when the stress is applied gradually on a material, on a member, will be known as strain energy. Right? Let us say O, X, Y and Z. So it will be linear. So now what is the formula? What is the strain value? It is simple as the strain. That means it is given by sigma equals to P upon A. So don't forget the units, Newton per mm square. Right? So now we'll see the load which is applied suddenly. Suddenly applied load. So if you plot a graph for suddenly applied load, so deflection on x-axis again and load on y-axis, that is P delta L, let us say x, y axis, it will be a square graph. So this part is So when you increase the load, the deflection is also going to increase and it will be squared. This is nothing but strain energy, right? And what is the formula for this? How you define stress? It is in the case of gradually applied load, it is linear and it is load upon area. So it is double this gradually applied load. That is why it will become sigma 2p upon A, right? Newton per mm square. 2p upon A. For normally applied, the gradually applied load, it will be p upon A. So remember this, right? Now we'll see impact load. Impact load. So the expression for impact load is little bit complicated. Try to memorize this. That is sigma equals to p upon A plus under root of p upon A whole square plus 2EP H upon A multiplied by L. So here L is the length, height, H is the height and P is the load, A is the Young's modulus and A is the area of cross section, right? This is the expression for impact loading, right? We'll see a problem on strain energy in next class. Don't forget to like, subscribe and share the videos. It's free.